I'm audible, right? Yes. Okay. So what I want to do in this session is try to give you the flavor of SOLEX data. So whatever theory that Manju ma'am taught us, we'll try to use it in the actual data sense. So I'll be giving you what kind of data we get from the SOLEX and what kind of spectral analysis we can do with the SOLEX data, particularly during flares. Okay. So yeah. So let me. I can skip this slide. So SOLEX, as name suggests, is a solar low energy X-ray spectrometer, which operates in the energy range of 2 to 22 keV, which is soft X-ray. Right. So there are some details. I'll just keep it. And I just want to reiterate the specifications that Manju ma'am also talked about, which are specifically for the SOLEX. Okay, so energy range is 2 to 22 kV. So lower energy, you might have heard some kind of different numbers for the lower energy. So currently we are fixing it around 2 kV, and for spectral analysis, it's around 2.8 kV. So the lower energy, we are trying to really try to understand what is the response of the instrument. So we're just trying to figure it out. Okay, so what we recommend is if you want to do spectral analysis, use it about 2.8 kV till 22 kV. Energy resolution is, of course, around 170 eV at 5.9 kV. So at 6 kV, if the two energy lines are about 170 eV apart, you can resolve them. Time cadence, there are, okay, so there are two channels here in the SOLEX. One is called fast channel or temporal channel. One is called spectral channel. Uh, so Manju ma'am talk about you get the electron and hole pair, you get the charge. After charge sensitive preamplifier, you get the voltage. So what you do with this voltage, it is still in the analog domain. So how do you process that? So from voltage signal to energy, how do you convert it? And how fast do you convert it? Because soft X-rays, we know it's a huge flux, right? So there are about 10 power 5, 10 power 6 counts per second, that kind of flux we want to process. So what we do, we segregate our what do I call it? The pulse detection mode in two channels. One is called temporal channel, where what we do is how many counts, how many photons that are incident on the detector is what we count. And another one is called the spectral channel or slow channel. So what we are interested more is what is the energy of the photon that is incident on our detector. So that's kind of slow. So it doesn't really count all the photons that are incident on it, but it counts the energy of the photon very accurately. Otherwise, there is another second channel, which is temporal channel, which counts all the photons that are incident, but doesn't care what is the energy of the photon. Okay, so we kind of combine these two channels and try to build up a very fast and spectrally accurate detector as well. Both we have 1 second cadence, but no. So shaping, if I could. So you have in the analog domain what Manju ma'am told. Yeah. So you. Okay. So this is the signal output of the signal that you get from the detector. So from here, how do you get to the energy of the photon? So you in between there is something called digital pulse processing. Okay, and from here you get the triangular. So what you intend is a triangular shape, and the width of that triangle is the shaping time of your triangle. Okay, so how fast you want to shape this triangle from this shape to a triangular shape? How fast do you want to shape it? So the slower you do it, the height of this triangular pulse or pulse height, which is equivalent to the energy of the photon. The slower you do it, you accurately measure the height of the triangle. The faster you do it, you have uncertainty in the height of this triangle. But faster you do it, you count more events. Right? So how fast do you process this chain determines if it is a temporal channel or the spectral channel. Right? So we have one fast channel, which is temporal channel. We just count the number of photons that are coming in. One is slow channel. We count what is the energy of the photon. Right. So one has more dead time is what we call it. So we are missing a lot of photons in the spectral channel, in the slow channel, but we know our spectrum is okay, accurate, very accurate. So we kind of take the spectrum from the spectral channel and take the count rate from the temporal channel, and we just kind of combine them and get a kind of accurate both temporal as well as spectral data. Right. Okay, so of course we are using silicon depth detector. We are using two detectors. We are calling it SDD1 and 2. So whenever you can download the data, let me just mention you can download the SOLEX data from July 2024 to December 2024. And the naming we follow is one detector called SDD1 and another is called SDD2. So if you look at the aperture area, SDD1 is the bigger aperture area and SDD2 is the smaller aperture area. So as we know, currently we are in the solar maximum. Most of the data or all of the data is from the SDD2. SDD1, it's kind of very high count rate for SDD1 to detect anything. So what we are releasing is only SDD2 data, which is of the smaller aperture, right? And rest of the details, I think Manju ma'am covered it, so I'll just skip it. I can move forward. Okay, so I can, similar to what Janmajay talked about SUIT data, I can talk about SOLEX data as well. We get the very raw binary L0 data, which is sent to ISSDC from the satellite and which is converted there, and it is sent to payload operations center, which is for SOLEX, it is situated in the URF satellite center. We process this L0 data and we convert it into a calibrated level 1 data, L1 data. So we have basically two types of files in the SOLEX. One is called light curve data and another one is called type 2 pulse height amplitude or PHA file. Okay, so what light curve data entails is the kind of temporal data that we get, right? So we have all this fast channel temporal data is stored in the light curve file, and all the spectral data is stored in the PI file or PHA file. Okay. So yeah, so to spectrally analyze the SOLEX data, what you need is all these three data sets. One is the light curve, another one is spectral, and third one is the calibration data set. So calibration database is exactly what Manju ma'am told. It's the response function, it's the ARF and RMF. Right. So let us try to look one by one what kind of data is available. So this is what I'm showing is a Jupyter notebook. It's all the data it's live, it's loaded. I'll be showing a lot of codes as well. If you want to play around with some numbers, we can do it. So just, yeah, it's an interactive session. Okay. Let me know if you want to just change some number. Let's see what happens. We can do that. Okay, let's start with the light curve data. Okay, let me just spend some time in the naming convention as well. So all the SOLEX data is of 1 day data. So L1 data will be of a single day. And the naming will be AL1, stands for Aditya-L1, SOLEX 2024-02-12. So this is 12 February 2024 data. It's a SDD2 data, which is of the smaller aperture. And it's a light curve L1 data file. And it's a light curve type data set. So it's again a FITS file. So you can use any standard FITS viewing application and you'll be able to open it. So I'm using, it's for NIT. Yeah. And of course you can use AstroPy's FITS routines to open the data and view the data as well. And if you just plot the data, this is what it will look like. Because of this slide, this is not visible. Anyway. Okay, anyway. So let me, forget about it. So this is what the entire 1 day data in the light curve data looks like. So you have all these different flares that are visible in the entire day. So this starts from 00 on the 12th February and it ends on 00 on 13th February, right? So on the y-axis, you have something called SOLEX counts per second. So this is very arbitrary unit. What does SOLEX counts mean? It doesn't make any standard. It's not a standard unit, right? So let's see how we can convert it into some physical standard units as well. But anyway, relatively, you can see there are some intense bursts. There are some slow varying bursts as well. So all of these are flares. And the cadence at which this data is available is 1 second, right? So if you look at the kind of background levels, you see there is huge variation in the background. There is some almost from 700, 800 to about 1000 variation. So why this noise is there? Can anyone tell me? Why is there is so much variation? What kind of statistics do they follow? So we are basically counting the number of photons, so it follows the Poisson statistics. So whatever variation we have is the Poisson error. So if you just bin the data, if you try to rebin the data, say for 60 seconds, and try to see what kind of light curve we see this kind of light curve. So it's basically we are trying to smoothen the data. We are trying to build the signal to our data and try to see what kind of variations are there. So you try to see there are some small signatures are there which were not visible in the 1 second cadence data, but are visible in the 60 second cadence data. So there are these small oscillations which can be flares, can be some oscillations as well. There are this another flare which was definitely not visible in the blue 1 second cadence data, but it is visible in the 60 seconds data. And of course, we can add errors on this data as well, which is again Poissonian statistic. And this is what the one entire full day data looks like. There are several flares that are happening in the in one day of the various flare energies as well. So let's come back to the spectral data. Right. So light curve data. Any question about light curve data? No, right. Yeah. Let's move on to the spectral data. So what spectral data has is the energy information. So what we saw here is just total number of counts observed by SOLEX per second. We don't know what is the energy of all these counts, right? So what we are interested, what physics, what data has more physics is the spectral data. What is spectrum, right? So this is one spectral data. Again, if you look at the, okay, this is some subset of the spectral data. What you will get is the L1 SOLEX year, month, date, SDD2, L1 .pi.gz. Okay, so it will have again 1 second spectrum at 1 second cadence, right? So it will have 86,400 spectrum file. So it's a type 2 PI because every row will have a spectrum, 1 second spectrum. If you look at the header, there are some different useful headers that are there. It's a OGIP compliant PHA data. It's a type 2. It's a type 2 format. It's SDD2, and there are some useful parameters which we'll go into details during the project time. Okay. And this is what the spectrum looks like. Right. So I've chosen some random 1 second spectrum data. So blue is one, and another one is the green. So immediately you can identify some of the features that Manju ma'am was talking about. You have this kind of continuum in both the cases, and you have some kind of emission signal here. But x-axis is very arbitrary. It's not visible here, but it's in the channel space. And y-axis is counts per channel. So these are kind of arbitrary numbers. We don't know what physically what do they mean. Right. So for us to understand what this number physically means, we have to have something called instrument response. Right. So there are two main files that we need to have to do spectral analysis with SOLEX. One is called response matrix function, or SRF, or IRF, or RMF. I mean, it has many names. You can call it anything. And another one is called ARF, or effective area. Right. So let's see how the response matrix function looks like. Yeah. So ma'am also showed one image, one rather plot. This is another plot. This is exact database of the SOLEX for SDD2. So what we have, if you have input energy of say 6.4 kV, which is in the purple, what you see in the detector is actually in the purple. So you have main peak, which is at 6.4 kV, and you have something called escape peak at 6.4 minus 1.7. I will not go into the details, but these are the different parts of the response that you need to take care of. And if you look at the matrix, so ultimately it's a matrix at every energy. So this is y-axis is the energy in, and x-axis is the energy out. So at every monoenergetic incident energy, what the response looks like is what this matrix tells us. Right. So for example, if you have input energy of 10 kV, you have output energy of 10 kV, and there is Gaussian around it, and you have another peak which is called escape peak here, and there is Gaussian around it as well. Right. So this is the first calibration database. Any question? Yeah. Yeah. So this is called escape peak. So what happens? I think Manju ma'am did not cover it. So any detector, there is. So for example, there is a silicon. We are using silicon detector. Right? So photon is incident on it, but it can happen that there are characteristic X-ray photons associated with every element. Right? K alpha, K beta. You know this K alpha, K beta, right? So the silicon K alpha energy. So what happens if there is a X-ray photon that is incident on the active volume, which is made of silicon? It can create K alpha photon. It can basically the photon can knock down the K shell electron, and that K shell electron can be that vacancy can be used by some M shell electron or L shell electron, and that photon that can escape from the active volume that is not detected here. Correct. So say you have energy of E, so there is a photon of 1.79 that is coming out that is not detected by the detector at all. So E minus that 1.79 energy, that makes another peak there. So what you are essentially measuring is E minus 1.79. If that photon goes out, the amount of charge that you are trying to measure, that is being measured by the detector, is E minus 1.7. So there is a peak which is called escape peak. Right. So all this difference between energy of main peak and the escape peak is always constant, which is equivalent to silicon K alpha. Okay. So there are, of course, other components, other non-Gaussian components there as well, which we are not currently using, but they are there. But they are not significant enough that we need to take care of them, at least during the solar maximum. If you want to do some Quaidson analysis or some lower spectral and lower flare, lower class flare analysis, you need to take care of all these non-Gaussian components as well. Right. Yeah. So the next second calibration database that you need to be aware of is called effective area, which essentially looks like this. Again, so x-axis is energy, y-axis is in the centimeter square. So what you essentially have is the quantum efficiency multiplied by your effective area, which I think Manju ma'am has equation somewhere here. So you see at around 5 to 10 kV, you have almost 100% efficiency, and your effective area is almost equivalent to your geometric area. And your efficiency drops down below 5 kV, 4 kV to almost zero, and above around 10 kV or so, it again drops down. So what it means, your instrument is very sensitive. It's almost 100% sensitive during this 5 to 10 kV, but the sensitivity decreases as your energy increases, or it decreases below some 2 to 1 kV or so. Right. So it is very efficient in this energy range. Right. So we can use this to RMF and ARF files. And okay, let us just load the RMF file and let us see what happens. So we can load the RMF file and we can convert the x-axis to energy scale now. Right. So what RMF tells you is what is the channel to energy relationship. Right. So raw data you have in the channel space, and RMF, what RMF tells you is what is the relationship between channel and energy. So once you load, so you can, there are several spectral analysis softwares, and once you load your spectrum and your RMF, your data will be converted into energy space. Right. So this is what the one spectrum looks like in the energy space. Again, you can see there is kind of power, not power law, but yeah, almost power law, and there is some emission here as well, which is about 6.4 kV. Right. So we'll come back to this. Okay, so we can use this instrument response and try to convert. So our light curve, previously, if you saw light curve, yeah, it was y-axis was in SOLEX counts per second. So we know what is the efficiency of our detector, and we can try to invert it and try to see what is we can try to convert the SOLEX counts into absolute physical flux units as well. And that is what exactly we have done. And we can now plot it in terms of flux in watts per meter square, and x-axis is time. Again, okay, it's not probably visible. There is no way to get rid of this top line, right? Because of this, that it's not. Okay, anyway, fine. Yeah. So again, y-axis you have in the flux, physical flux units, right? Which is, so I have plotted this in the energy range of 0.5 to 4 angstrom. Anyone know the significance of this wavelength range, 0.5 to 4 angstrom? Why is it 0.5 to 4 angstrom? Okay, I'll come back to this. Okay. Yes. Okay. Let us talk about flare detection first. So you can see there are lots of flares that are happening during the day. But how do you detect these flares? So what are the different mechanisms, different algorithms you can think of to detect the flares? You want to take a guess? Sorry? Yeah. So, but how do you identify peaks? I mean, is it a peak? Okay. So if I say threshold is here, I'm missing all these flares. So it's a challenging problem, and it's still people are coming up with the new algorithms to try to detect the flare automatically. And the number of flares detected, it has very interesting implications in the standing problem of coronal heating problem. So what Krishna talked about is the coronal heating problem, where the temperature of the corona is about million degree Kelvin, which is not explained. And one theory is because you have omnipresent small flares are all the time happening in the solar corona, and which can impart the necessary energy in the corona to sustain that kind of temperatures. So if you want to, so you want to measure all these small scale flares and try to build a graph and see if there are enough number of these kind of flares that can sustain the temperature of the corona. So it's a very challenging problem, and people are still working on this. Right. So yeah, I have some flare detection algorithm as well, and I just run it. And as you can see, I am missing also quite a lot of flares. So this flare, this is definitely another flare which I'm missing. There is this small scale flare I'm missing. There are probably these flares there I'm missing as well. Okay. So probably if you have some more ideas, you can work on it. We can collaborate. We can go. Okay. Yeah. So coming to the answer, why 0.5 to 4 angstrom? It's from the GOES time series, which Manju ma'am talked about. So GOES, which is traditionally been observed to detect the flares in the soft X-rays, it has two energy bands, 0.5 to 4 angstrom and 1 to 8 angstrom. Plot is not visible. What is this cross in the left? That cross is yours? No, that is my cross. That is okay. Let me just. I think this is okay. Fine. Is this readable, visible? Okay. Fine. Okay. Yeah. So for the same day, if you overplot with the GOES data and SOLEX data, you see there is very nice agreement between SOLEX and GOES in the energy range of 0.5 to 4. Right. So we don't have the capabilities to make the light curve in the energy range in the wavelength range of 1 to 8 angstrom, but we have our detection capabilities in the 0.5 to 4 angstrom. But traditionally, all the classes of the flare is defined by this the flux in energy band of 1 to 8 angstrom. Right. So how do you? So what is the class of this flare? This particular flare, which is the strongest flare of the day? M6. Yeah, which I've been using. I think you guys know this particular flare. Yeah. So this is M6 class flare. Right. So let us go ahead and try to take this flare as an example and see what kind of spectral analysis we can do. Okay. 1 to 8 angstrom is 1.2 to 12 kV. So between 1 to 2 kV, we have response issues. So we can get it probably. We need to have some scale factors, but we are not too sure. It's not standard. Yeah, that's the only case. It's not standard. So standard is always 1 to 8 angstrom, which goes is continuing. Right. So probably we can make our own standard. Correct. Yeah. So what is better nomenclature is probably temperature and emission measure, which is kind of global rather than flux in some arbitrary energy range. Right. Yeah. Okay. So let us zoom into this particular flare, which is M6 class flare. Right. You have starting at around 330, you are peaking at around 347, and end, which you can define arbitrarily, is I'm defining at around 350 or so, 350 or so. Right. So you have SOLEX data, you have Guwahati data. I've just overplotted as well. And since SOLEX being spectrogram, we can try to get the light curve in different energy ranges as well. Right. So I've just plotted the light curve in 3 different energy ranges, which is 3 to 6, 6 to 10, and 10 to 15. So can you see some difference in the light curve? Right. So as you can see, it's not very evident here, but 10 to 15, this light curve peaks slightly earlier than this blue light curve. So what is happening here? 10 to 15 being the harder energy range, it is probing more non-thermal part of the spectrum than this 3 to 6 kV, which is probing the thermal part of the spectrum. Right. And non-thermal, of course, as Manju ma'am said, comes before the thermal spectrum. Right. Right. So this is exactly what is being observed by SOLEX as well. Yeah. Rate curve. Okay. So if you go back to your efficiency curve, your efficiency is very poor at about 10 kV. Right. So it's your number of counts that are detected in SOLEX is poor. So more fluctuations means more error in the observed counts. Right. If you even look at the spectrum, above 10 kV, you have very few counts. Right. So these are all just errors in the detection. So if you probably integrate for more duration, you'll see a smoother curve. But the integration required for say 3 to 6 kV and 10 to 15 kV will be different if you want similar smoothness to your curve. And they're impulsive in nature as well. I mean, the harder you go, they are more impulsive in nature, as Manju ma'am told. Right? And these are inherently smoother in nature. Okay. So this is what we'll go into the detail during the project time. So how do you have the spectrum? How do you do spectral analysis? How do you fit the spectrum? Right. So I'm just trying to demonstrate here how do you take one spectrum and how do you do spectral analysis with it. So I've taken one small integration of the spectrum during peak of the flare, which you can see in this shaded region. I'm not sure if it is visible, but during peak of the flare, if you take around 30 seconds of spectrum and try to integrate it, this is what it will look like. Yeah. So let's see and understand what features do we have here. So we have this background continuum, which looks like a power law, but not exactly power law. We have one emission line here, we have one emission line here. We have kind of some feature here. We have another small emission line here, another small emission line. So what are the different parameters that we can try to estimate with this temperature? As borrowing from the Manju ma'am's lecture. What are the different parameters we can measure? One thing we can measure is temperature, which is given by the continuum, which is thermal Bremsstrahlung basically. Another thing, so this is ion complex. So this entire line is coming mainly from the different ionization state of ions. This is iron nickel complex. So we can get the abundance of iron and iron nickel. This is calcium complex or calcium line particularly. So, and this is argon line. So at least from 2.8 kV, till around 8 kV, we have the lines of argon, calcium, iron, and nickel. So we can get the abundances of all these lines as well as temperature. Right. This blend of multiple lines. So these two lines are, I mean, there are hundreds of lines there, but we don't have resolution enough to resolve them. It looks like a single line. But you can still do, but these are mostly iron lines. Yeah. These are mostly iron lines, so you can assume a kind of single abundance for the iron and try to estimate what is that abundance of iron. They are single lines. They are almost singles. I'm not sure they're single lines. I think there are also some multiple lines, but it's not as dense as iron complex. Yeah. Okay. So yeah, this is exactly the thermal Bremsstrahlin equation that Manju ma'am told. And there are some database of all the abundances that are available as well. So you can see this is the table of abundances that are, it's a collection of all the observations that has been done till now, and people have estimated what are the abundances of different elements that are available in the corona. So the first column is the atomic number 1, 2. So 1, as you can see, is all 1. So it's in reference with the hydrogen. And you can see 26 is here. Yeah, the last row is the 26, which is the kind of after hydrogen and helium, it's kind of next abundant element, which is about 6 into 10 power minus 5 of that order. Right. So even if these elements are present in traces, they are abundant enough to give the emission lines. Right. And different databases rather than models, different databases. So I think the latest one which we use is this sun coronal extended, which is kind of a correlation of all the different observations. Right. And there is a kind of good agreement between different databases as well. So some elements will have slightly different numbers, but the prominent elements will have very good agreement between them. And of course, we know the photospheric and coronal abundances are quite different. Right, we'll come to that as well. Okay, so we can just code this model, thermal Bremsstrahlin plus emission lines. We can just code it and try to see what kind of simulated spectrum we get. So this is exactly the plot that Manju ma'am showed. We can simulate it and try to see what kind of spectrum is available for different temperatures. Right, and so this is the simulation. And and of course, what we see is not the simulated spectrum, but the convolution of the simulated spectrum with your response of the instrument, right? So what we really observe is something like this. So 5 megakelvin is somewhere here, 10 megakelvin is here, 20 is here, 30 is here, and what you see in the yellow is the observation. So we can try to estimate what should be the temperature of this observed spectrum. So what should be the temperature here? It should be somewhere between 10 to 20 and closer to 20. Right. So this is about 20 megakelvin. But how do you exactly estimate what is the temperature of this spectrum? So to do that, we do something called the fit forward. We use something called forward fitting. Okay. For forward fitting, there are several spectral fitting softwares that are available. One is called XSpec, Specs, ISIS, or Sherpa. So what I'm currently showing is Sherpa, but what we'll be using for the project work is something called XSpec. Okay, so tomorrow we'll be using XSpec. So let me just skip it, and so this is something the fit looks like with the chi-square. Yeah, so this is what it looks like with the chi-square about around 2.87. So is this a good fit? What is the typical chi-square that you expect if it is a good fit? Around 1, right? So it's slightly higher, and you see there are some residuals here as well. So what I've not done included here is the abundances. So I fixed the abundances. I'm just trying to estimate the temperature of the model, temperature of this particular observation, right? Which is not sufficient. I need to vary the abundances as well. And if I vary the abundances, Okay, let me skip this error analysis. If I vary the abundances as well and try to estimate the temperature and the abundances of these three elements, so it's a relatively better fit with the chi-square of about 1.38, right? You have good fit of the lines as well and the continuum as well. So you have temperature of about 19 megakelvin, which we expected about 20 megakelvin. You have emission measure, which is basically the amount of plasma, amount of volume that is present during the flare. So you have this much amount of plasma at the temperature of about 20 megakelvin. You have the abundance of Fe is something called 1.44. So what is the unit of this 1.44? So what we do is we measure the abundances in the units of photospheric abundances, fixed photospheric abundances. So photospheric abundances do not change during flares; they are mostly constant. But coronal abundances of all the elements, they change during the flare because of all this dynamics that is happening during the flares. All these, they get ionized, they get recombined, and these abundances changes. So we measure the abundances in the ratio of the photospheric abundances. So we have about 1.44 of Fe abundances, which is 1.44 of the photospheric ion abundances, 1.85 of calcium, and about 9.91 of 0.9 of argon abundance. Yeah. I mean, we have lines coming from these three elements majorly. Yeah. But mostly all are coming from ion only. Different ionization level, but all are ion. We assume that all the at least the ion species abundance is set. And correct. And the emission line is only dependent upon the temperature. Exactly. Yeah. Okay. So this is for one particular spectrum that we did this. Yeah. Currently, there are only 5. So if you decrease your fitting energy, there are more lines here as well, and the number of parameters become more and more, and it becomes very difficult. And currently I'm trying to fit with the single temperature, which is, I mean, it's a good approximation at this energy ranges, but it's not exactly correctly accurately depicting the picture. It's a very multi-thermal plasma. And what we are trying to do is we are approximating that all the flaring plasma that we are observing is at the single temperature, which is exactly not true, but okay, it's a good enough approximation, and we are getting some good enough chi-square as well. And yeah, of course, it's yeah. I mean, this is the integration time. So it's a M6 class flare, and okay. So it's a peak of the M6 class. Yes, I'll come to that. Yeah, I just want to highlight this. All models are wrong. Some are useful. Okay, this is the disclaimer. Yeah, and okay, and if we try to, okay, I have to go into the full scale. Yeah, okay. So if we do this spectral analysis across the flare, this is what it will look like. Right? So you can start for the non-flaring mode. You see how the spectrum changes. Right. So what are the parameters? How is the shape of the spectrum changing as a function of flaring phase? So one thing we can quickly observe is the intensity of this emission line, ion emission line, that is changing. Right. Let me play it again. So during non-flares, you have almost no emission lines. It starts to get intense, and it's very intense during peak of the flare. You have this emission line coming up as well, and as flare is dying down, the intensity comes down, and this ion nickel complex intensity is almost zero. And as it dies down, there is almost no intensity of this ion. Okay, peak is not shifting, it's the x-axis that is, okay, it's not at the constant x-axis. It's at the same energy, it's not shifting. It's just a plotting artifact. Okay. Another thing which you can see is the probably slope of this kind of power law, which is basically tells you what is the temperature. That is also changing. As you can see, it's very harder during the peak of the flare. That means your temperature is very high during the peak of the flare, and it starts to come down as you are in the decay phase. Like it starts with very low value as well. It kind of picks up to around 20 megakelvin, and it kind of decay down. So what you can do is you have all the fit parameters across at the different duration of the flare, and you can see how these fit parameters evolve during the flare. So this is the temperature evolution during a flare. And in the background gray, I have just plotted the background flux during this flare as well. So you see at the start of during the quiescent period, you have the temperature about 5 megakelvin, and it slowly increases, and pre-flare level it has around 10 megakelvin, and it suddenly shoots up within about 30 seconds or a minute so to about 18 megakelvin. It reaches peak at around 20 megakelvin before the peak of the soft X-ray flux peak, and it decays down and settles down to about 5 megakelvin value as well. Right. So this is the evolution of temperature, how it should look like. This is a typical flare. If you look at the emission measure, okay, it's not very good plot, but if you look at the emission measure, it starts at around almost zero. So there is 5. Okay, I should have plotted this in the logarithmic scale, but there is some value of emission measure at 5 megakelvin during P flare. It kind of shoots up during the flare. It peaks and it again dies down, and it's slightly more than the pre-flare levels. And as you can observe here, the peak of the emission measure is after the peak of the temperature and after the peak of the soft X-ray flux as well. So this is because as flare is initiated, all the non-thermal particles are hitting down on the chromosphere or the lower atmosphere. Your temperature suddenly increases. So what peaks first is the temperature, but there is not enough plasma that is at the high temperature. That you have very low plasma, very low volume of the plasma at high temperature. Your temperature peaks first, and then your flux is also building up. So your flux peaks next, and as the temperature is building up, all the plasma occupies the coronal loop that you saw in the movie, and then as the plasma is occupying the loop, your emission measure picks up. Right. So temperature, and then soft X-ray flux, and then emission measure. So this is typically what the flare looks like. And if you look at the evolution of the, say, ion abundances, this is what it looks like. So there is something called FIP effect. I'm not sure anyone touched about it. Yeah, I'm not sure. Should I go into this? Maybe not, right? Probably we'll go into this during the project. I'll just skip it. So this is again a typical abundance profile during a flare, right? So during a quiet period, it has higher abundances, though the intensity increases during the flare of the ion emission line. The abundance decreases and then comes back up again. This is called first ionization potential effect, or other inverse first ionization potential effect, which probably will go into during our project time. Okay. Yeah, that's about it. I'll just conclude here. Thank you. I have to ask lots of questions. Yeah, good question. Okay, so just to reiterate the question, he's asking free parameters. What are the number of free parameters during, say, pre-flare, peak of the flare, and post-flare as well? So it depends. So as you're probably looking into this movie as well, I'm not my even my higher energy range till where I'm fitting. That is also variable. That is also changing. So it depends how much signal you have. So during peak of the flare, you have a lot of signal. You have signal till say 12 kV, 15 kV. You can fit till 15 kV. But during say post flare or pre flare, you don't have a lot of signal. So I just limit myself to around 6 kV, 7 kV, and I don't have a lot of emission line signal as well. So I can't really estimate what is the abundance of different elements as well. So I just kind of fix it. I assume it is quite some what the database suggests, that is the value. I kind of fix it and just try to estimate the temperature, emission measure value. That's it. So that's some internal parameters. So if there are no lines, I fix it and try to estimate the temperature and emission measure. That's it.
Any more questions? You have to do a project on that. So no more questions. Otherwise, we will ask you questions at the end of the workshop while you are present. So yes. You have difference in how the temperature varies and how the density varies.
Correct. Yeah.
The emission.
So
why is that the emission measure curve is very narrow? What does it mean?
Probably it's not a good plot. Yeah, it's not narrow. Okay. Yeah, I should. Okay, let me plot. Yeah, I can plot it.
I can be in the log scale or.
Yeah, that is actually better. Okay, it's an image file. Okay.
If you change the scale, perhaps it will be.
Yeah, it will look better. So what happens? So there is paper by Hudson. So he talks about if you plot temperature versus emission measure, it follows a kind of typical curve. So what you have is you start with the kind of low emission measure, temperature fix first, and you have very small amount of plasma with high temperature, and the temperature is decaying down, but the amount of plasma that is there at the higher temperature increases. So your loop kind of fills up, but your temperature is decreasing. So this is what it's showing, the temperature and emission measure.
Once the loop fills up, it radiates.
Correct. And it kind of stays at some constant value. So your loop is filled with that plasma, but your temperature is decreasing. Right. So emission measure is kind of constant.
More questions?
Yeah. What can you derive from abundance? Yeah, it tells you how much amount of plasma is there at that particular temperature. But as you saw, the SOLEX is not an imaging instrument, right? So we don't know how much volume of the plasma is really at that temperature. So we need some kind of extreme ultraviolet images to give you some context of what kind of flare and what kind of volume that is flaring. It kind of tells you what kind of thermal energy is there, but we need some volume parameter as well. So it helps us calculating what kind of thermal energy is there. Temperature doesn't give you what kind of thermal energy is there. You need amount of plasma that is present as well. So yeah.
More questions? If not, you can continue basically.
Yes. Yes. Pointer. A pointer.
Yeah, you can also use the mic if you want to stay at one position. It is mainly useful.
एसी बंद किया क्या? पसीना पसीना हो रहा था। एसी बंद कर दिया। एसी बंद। कभी तो स्क्रीन वाइब्रेट नहीं रहता। सारे बंद कर लो। पूरी रात से। अच्छा।